Okay, my name is Rohan Naidu. I am a first-year Pappalardo fellow here. Before I start, I wanted to really thank the Pappalardo Fellowship, Neil and Jane in particular. It is one of the key reasons I chose to come to MIT. As many of you know, academia can be a very exciting but also very lonely business. And the fact that there was this fellowship here that was not just in the form of all these fantastic folks we've heard from today, but also spanning so many generations was something that MIT really uniquely offers incoming postdocs. And so thank you so much for that. Thank you so much for making it happen. And thank you for letting me be the next link in this chain that stretches back so many names in my field that I really look up to. So today I'm going to tell you about the first glimpse of the very first galaxies that JWST is showing us and all the surprises we're finding at these unprecedented redshifts and epochs that we're now able to finally see for the first time. So before we get started, here's one of my favorite plots across all of astrophysics. We see it a lot, but yeah, when I first came across it, it gave me goosebumps because in these few pixels, we really have the whole history of our universe. So we're starting on the very left. This is this greenish afterglow of the Big Bang, the beginning of the universe, following which the universe is plunged into this ocean of darkness. There's no starlight. It's just this vast ocean of dark neutral hydrogen. And then something remarkable happens. These first points of light start to glow. These are the first stars and the first galaxies coming alive. And they start carving these bubbles of ionized gas around themselves. So this grand epoch of reionization that Christina talked about in great detail today, this era of great change. All these bubbles coalesce. The universe is reionized. And today we are sitting in a galaxy like this one, all the way to the right, trying to make sense of this grand story that has unraveled in our past and given rise to us. As grand as this sounds, as beautifully as this is predicted, as exquisitely as this story is told, it's still very much a story in the sense that this vast epoch of the universe is vastly uncharted to first order in terms of all the current data we have. Right? So we know the Big Bang happened from the cosmic microwave background and such. But after that, we barely have any data in some sense, and all the way in the first billion years. And then again, around the Milky Way and the local universe, we have a much better picture of what's going on. And so this has been the state of affairs for a fairly long time. But what we really want to do is we want to pierce this veil. We want to really search for these first galaxies in this first billion years of the universe. We want to see how we went from this darkness to first light. The search for the first galaxies works somewhat like this and is somewhat possible. So here I'm showing you this movie that the Japanese national broadcasters decided that we had to educate everybody about the first galaxies, which are represented here as this tiny little baby. We here are the observers looking out into the past with our binoculars. And the idea here is that these galaxies, these very distant ones, we are still able to perceive them in their infancy, even though they have since evolved, right? So these galaxies are growing up. They're going through their youth. They're going to MIT. They're starting a medical technology company. They're endowing a famous fellowship. They're going through life. But we're still able to perceive their very infant epochs. And so even though these galaxies have evolved, we're still able to see them as they were first forming right after the Big Bang. And this is really quite a mind-bendy concept, right? What we're doing is we are able to perceive the universe, kind of everything, everywhere, all at once, right? So this is kind of crazy. It's almost like if I'm staring very hard out of this window right here, and I just stare intently at that patch of the sky in an astronomy sense, very close to me, I'm seeing, Tom Brady making his debut for the first time. He's still, undivorced, unfrazzled, seems, life is going well, everything's happy. Farther out of the window, you see the Boston Tea Party happening live, right? Like we're protesting no, taxation without representation and such. And even farther away on the Boston Green, we have the dinosaurs romping around as they were. And so that's something astronomers can do, right? Like we are able to perceive the entire expanse of history happening simultaneously. So we are able to see galaxies like ours, this very evolved Tom Brady-esque creature, and we are also able to see the equivalent of these dinosaurs, these very, very first objects of light in the universe simultaneously. The way this works, when we are trying to look for these very first, very early systems, here I'm going to show you an example in terms of how this actually works, in terms of what kind of data we get and how we search for these objects. So here I'm going to show you the same galaxy. This is a simulation. It's a movie, where I'm going to move this galaxy to larger and larger distances, to earlier and earlier times in the universe. And what I'll draw your attention to, so these here are filters, buckets of light, sensitive to very particular wavelengths. So these are visual optical wavelengths, so about 0.4 microns to about 0.7 microns, all the way out to about 1.6 microns. So these are filters that were installed on the Hubble Space Telescope, our eye in the sky for the last 2-3 decades. And what you'll see is as I move this galaxy to higher and higher redshifts, to larger distances, all its light basically shifts into the infrared. So there's two things that are happening. One is because of the expanding universe, light is redshifted from these very distant objects all the way into the infrared. The second thing that's happening is that these galaxies, these nascent infant galaxies, are ensconced and blanketed by this neutral hydrogen around them that completely snuffs out all their blue light. So a very characteristic signature of these distant sources is that they're detected only in these infrared bands, and then they completely disappear in all these blue filters because of these two effects. And so for the longest time, our farthest outpost in the universe, the most distant object, the frontier of our collective consciousness, was this galaxy called GNZ11. It's a galaxy that we really had to push Hubble all the way to its limit to find at a redshift of about 11, which is 400-ish million years after the Big Bang. This galaxy was found by Pascal Ush when I was an impressionable undergrad, a visiting student at Yale. So this discovery happened around me, a good fraction of the reason why I'm standing in front of you today talking about this topic. And so this galaxy really represented the farthest we could push. And then you know what I'm going to say, which is that we are now in the JWST era. So here I'm showing you a picture, my favorite one, of JWST, which is not the typical one where people see the sunshade and stuff, but this moment of when it's separated from the launch vehicle, and there's this beautiful shot of the Earth in the background, and we are seeing it off to its outpost. And then here is one of the first images that was released with Joe Biden looking so excited, almost as this is an ice cream truck parked right there, ready to start delivery. But that's what these images were like for us. They were an ice cream truck. And right away, it was very clear that JWST was going to deliver. This thing that we had waited for several decades to really push our cosmic frontiers was going to do it, and do it very easily. So here I'm showing you a galaxy I found within the first week of JWST data, really. Here I'm pointing it out. It's this tiny little dot that the arrow is centered on. You see, this source, this system, was completely invisible to us earlier. We would never have detected it at these lower infrared wavelengths that were available with the Hubble Space Telescope. We really needed JWST to see it. And so it really lights up at 2 micron, all the way out to 4 micron, but then it's completely invisible, this very smoking gun signature of very distant galaxies. Here I'm showing you kind of like a co-added image where I take all these redder bands and assign them a color, namely red, and other bands are assigned a color of green and blue. And so you see it really sticks out as this very compact little red dot because all its light is in the redder bands. So already we were able to find galaxies farther than we had ever seen before with these early JWST data. Further, the properties of these galaxies were really surprising and mind-boggling. Namely, they were extremely luminous and appeared to hold much more mass than anybody had predicted. So here I'm showing you these two galaxies that we called Glass Z11 and Glass Z13. If I could, of course, I would name them after you, Neil, but the convention in our field is to say that, glass is basically the patch of the sky, and then Z11 refers to the redshift that we've estimated for it, for how distant it is. And this is something I hadn't fully appreciated, but there just was so much appetite for these results when they first came out. It was so exciting to see how excited everybody else was about this. And so there was just so much coverage of these first galaxy results and the fact that we could peer back farther into time than we'd ever been before. And this is an article that actually Neil pointed out to me when I visited him over Christmas for dinner. I hadn't known that there was this article in Scientific American, but Neil had very kindly folded the page and was like, hey, tell me about this. How did you make this picture? And so, shout out to you. Here's one of these articles that got me into a lot of trouble, actually. I didn't realize you have to be very careful when you talk to journalists about what you're talking to them about. So I just someone was like, how did this discovery happen? What did you do? And I just told them everything. I was like, I was sitting on my couch. I found this thing. I messaged my collaborator. I called my girlfriend. She was too busy. She was watching TV. She was like, that looks totally unimpressive and unremarkable. And yeah, I'm still, I think she'll be here later for dinner, so I'm still hearing about this. The word underwhelming is a red line in the household. But yeah, it was also pretty exciting, Captain America retweeted this tiny little image that I made on my laptop. I woke up one morning and my Twitter was completely jammed with notifications because, Captain America himself, Chris Evans, turns out, is very, very interested in space science and tracks the Astronomy Archive and the latest news and such. And so he retweeted this article with this same JPEG image I was showing you earlier, where we stacked these images to produce this little red dot. But coming back to the science in terms of why these galaxies have proven so surprising and have really seized the community's imagination, it basically boils down to this. If you asked any simulation, the kinds of simulations that Mark runs, Mark Fuchsberger and company, if you asked any theorist, honest to God predictions that we put down in 2018, some of these with me and my friends, we essentially predicted we would find basically 0 plus or minus 0 galaxies that were so bright at these very high redshifts in this early data. And what we are finding, not only in these very early data, but now also analysis spanning the last full 6 months, is that we have tens of these candidates. And they seem to be very robust. They're solid. They pass all the checks. They've been found by multiple different teams. And so the question is, how? What is going on? So traditionally, we have been able to predict the counts of galaxies across a very wide range of cosmic time using these kind of very simple luminosity functions, named, of course, for Paul, who's sitting right here in the front row. Paul, I'm afraid to say that, you had a great run, but it seems that, now there's galaxies out there that don't seem to follow your very beautiful, simple rules. Yeah. We'll discuss that later. But here I'm showing you a plot of basically counts versus brightness. And the idea is that there's way more counts compared to what we predict, essentially. And that is the tension. Another way to think about this, your mental model for what this puzzle is about very early galaxies that are so bright, the idea is that we went into this early data expecting something like this. We were expecting to find this tiny, 4-year-old hoisted in his mother's arms. And instead, we found somebody who was, already had a PhD in astrophysics and was about to graduate. And so that's kind of like a rough mental model for why we were surprised, because we were expecting galaxies that were the equivalent of these infants. And we went out there and found, advanced degree holders. And of course, out of all this excitement, there's been no dearth of solutions for how we solve this problem that's overhanging the field. So there's been several classes of solutions. I'm just going to quickly summarize them. One class has been about, let us go and rework cosmology. Let's go rework dark matter. Let's look at what primordial black holes are doing to maybe early galaxy formation. Let us tweak with dark energy to buy more time for these galaxies to form at these very high redshifts. Another class of solutions, dearer to my heart, has to do with new astrophysics. let us look at what these very early generations of stars, POP3 stars, metal-free stars, stars that we haven't been able to perceive before, whose properties are completely unknown. Maybe they are able to explain why these galaxies are so bright, perhaps. The way we'll solve this is through detailed spectroscopy. So what we have right now is basically a grainy photo of a face in a large crowd. But what we really want to do is we want to do spectroscopy, which is we want to administer the equivalent of a 23andMe test and really figure out what really makes up these galaxies. So the first of this class of extremely bright galaxies has recently received this 23andMe treatment. And so here I'm showing you a spectrum, which is namely breaking up the light from that system into all its constituent elements. And you see all kinds of very exotic chemistry. So there's currently a paper being written almost every 2 days trying to explain what's going on inside these systems. And very soon, in about June, July, we will have spectra for tens of these sources. In fact, there's one coming in next weekend. So you know where to find me next weekend, namely on that same couch with the word underwhelmed banned from the house. Another way we can go about this, another approach that I'm trying to develop, which very much is kind of like taking inspiration from what Anna Frabel does over here, namely thinking like an archaeologist. So the analogy here, the kind of question we are trying to answer is when really were these first galaxies born? When did first light happen? When did this whole epoch go down? And so a helpful analogy is to think like an archaeologist. So imagine you're an archaeologist tasked with searching for the most ancient civilizations. So you have this world map here. You've been tasked, go find me the most ancient civilization. So what we've been doing by taking these extremely deep images with JWST is essentially picking a random spot and hoping we get lucky, right? So maybe you land in Africa and you're lucky, but maybe you land in the Atlantic Ocean and maybe you find Atlantis, but all the best with that, right? So what we can do is we can be smarter about where we dig, about where we choose to dig as archaeologists, right? So you could say that, hey, I believe ancient civilizations really flourished in places like Mesopotamia and the Indus Valley, where there was a lot of water, life was good, the plains were fertile, food was abundant, and so on. And so we choose to dig in the equivalents of these Indus valleys. And in a cosmological context, what these fertile river valleys are is basically overdensities. So overdensities are these huge agglomerations of dark matter and gas in the very early universe where the first stars are expected to be born. So what we want to do is we want to find overdensities like these and then really go digging there and do archaeology on the galaxies there to try and reconstruct essentially the very, very early universe and its past. And so this is an experiment that I've been approved to execute, and it's going to be, I just got a notification today that it's scheduled for also next weekend. So this data is going to be coming down next Sunday, where what we've done is we've found this very special spot in the universe, which looks like these very early overdensities, these very early river valleys. It's a really extraordinary patch of the sky where about 1/3 of all the most distant galaxies we know are all concentrated in this tiny patch of the sky. So it's a really special place. And so what we're doing there is we are going digging, basically. What we want to do is we are going to measure these 23andMe type of spectra for lots of these galaxies. And the idea there is we'll be able to tell the difference between galaxies that formed extremely early, that are very old, versus ones that are just coming into formation. So the idea is that we'll be able to backdate when star formation began in the universe by essentially asking how old are galaxies in this very special, very extreme place. So this is kind of like a complementary approach to just staring super hard and going directly chasing after these things, which of course we're also doing. And so what's next in terms of where do we go from here in terms of really understanding what's inside these first light systems, right? So what we're currently doing here, so I'm showing you kind of like the energy distribution of one of these very distant galaxies. And so we're able to probe essentially the rest optical spectra with JWST. We're able to find these objects. But what we really need to truly understand what's inside them, to really unambiguously see signatures of the very first stars, we need something like the Giant Magellan Telescope, the GMT. We'll be able to see features like Lyman alpha. We'll be able to see features from these very hot, very massive stars, features that you really only see in the UV because of the hotness of these objects. For that, we really need the GMT to complement JWST's forays out there. So the note that I want to end on is that it was not very long ago, only about 100 years ago, especially in the context of cosmic time, 100 years nothing, right? Where we were wondering whether even other galaxies exist, right? We were having the great debates, many of them out of here, out of the institutions in Cambridge. And so from that corner of the plot, where our consciousness was really limited to this galaxy, our galaxy, we are now standing on the precipice of really pushing all the way back to the brink of the Big Bang and finally filling in this missing chapter, finishing our entire cosmic history in terms of light, in terms of where everything began. And so that is the opportunity we have in the 2020s with JWST and facilities like the GMT. So yeah, that's the note I'd like to end on, and I'll take your questions. Thank you.
I want to know, when we talked in December, you had indicated that particular galaxy you saw was, I don't know, somewhere between 100 and 200 million years old, maybe even a little bit older. Has a spectrogram been taken of that particular galaxy? Because you use, I understood, the intensity of the 7 or so images that were taken through a filter, as opposed to a spectrogram of that galaxy.
Yeah, so...
And if it's been taken, has it confirmed your estimate using your personal computer?
So yeah, so that patch of the sky is going to be up again in July. So July-ish, end June, July-ish. So that's when we expect it'll be scheduled for. So stay tuned, and of course, I'll make sure I write you a note.
Let me know.
Yeah, absolutely.
Thank you.
Other questions? Sarah?
It's really amazing that just in the first short time, we have something brand new that wasn't anticipated. So I was wondering if there's room for more of that, or, I mean, obviously that's hard to predict, but I wanted to get your take on it.
Yeah, no, absolutely. We're barely getting started, right? So like a lot of the really exciting stuff till now has largely been in terms of taking photos, right? Like taking these coarse 7 filter things that Neil was alluding to. But now what's suddenly happening is data sets like the one Christina was showing earlier and other experiments I'm involved in are taking spectrograms for hundreds, thousands of galaxies. So once I'm going to be done with this and we're done with the dinner, I'm going to go back home and I have, order like 1,000 of these that I'm going to like sort through tonight and send them off to like, friends that I'm working with and so on. So we really are going to see the new exciting kinds of objects. There's several of these we're finding, right? Like extremely low mass black holes, really like super dusty, very massive galaxies at even intermediate redshifts, all sorts of objects, like there's a whole zoo of them that we're going to start finding from the spectra as well. So that's going to be a whole new wave that is basically like getting started like rightish now is something for you to look forward to in the coming weeks.
So it's clear from what you showed that before JWST, we weren't seeing the earliest galaxies. We were only seeing the earliest ones we could see. Do you think with JWST we'll see the earliest galaxies, or again, only the earliest ones we can see?
That's very much an open question, right? Because the dream is that you've finally basically run out of these things at some point. Most theories of when even baryons start condensing into light-emitting objects place that limit at about redshift 18 to 20-ish, which in principle we have the ability to probe, right? We have the instruments to probe. The only question is, are those things going to be intrinsically luminous enough for us to be able to pick them up in terms of sensitivity? Maybe we'll get lucky with gravitational lensing, or the universe maybe produces more of these extremely bright things all the way, even at those epochs. Maybe we get lucky, never say never, nowadays especially. So yeah, there is a real chance that we are able to do that. We are able to push past that limit.
Other questions? Stunned silence. Paul, do you want to make any additional defense of the Schechter function?
They're great. I love them.
The question is the input spectrum of perturbations, and we're agnostic on that. Once you start doing simulations, you commit yourself to what you're going to form. Okay, so the simulations don't produce it. We have tunable parameters and we can match anything, but we don't know what the physics is.
Dave.
You just mentioned dusty universes, and I guess I think of dust as being made of heavier elements. So when can you get dust if you start with hydrogen?
Yeah, no, that's a very exciting open question right now, because typically we produce dust through fairly evolved stars that are shedding off their outer layers. But what we're finding is that even out to redshifts of 7, 8, 9, so barely a few 100 million years after the universe has started, we still find objects that are cloaked in dust. And so the question is, where is that coming from? Because it can't come from these very evolved stars, because the universe is just too young for there to be any evolved stars. And so there has to be some other channel of dust production. People believe that supernovae might be able to make this kind of dust early on. So it has to happen from the death of these massive stars at early times is the idea. But it's very much a very open and very exciting area of inquiry, trying to figure out exactly that, where does it come from?
Okay, if there are no more questions, let's thank Rohan for this talk and all the speakers.